In this lecture, we will learn how to detect bimodal distributions, match measures of central tendency to their appropriate levels of data, and use the mean and median values to estimate the direction of a frequency skew. The pictures on this slide may not make sense yet, but when we explore Learning Objective 3.5, I'll try to make them relevant. As we continue talking about shapes of distributions, let's look at some examples of data sets and determine if they are bimodal distributions. Remember, bimodal distributions have two class intervals or scores with high frequency, separated by at least one class interval or score with low frequency. Let's practice identifying bimodal distributions using problem 3.2 from page 46 in your text. Begin by ordering the scores. For question 3.2a, the ordered scores would be 9, 9, 9, 10, 11, 12, 13, 14, 16, and 20. There's clearly only one mode for these data, the number 9. Thus, the distribution is not bimodal. If I looked at the distribution, it would be positively skewed because the majority of the values lie in the low range. The distribution in 3.2b is also not bimodal. The ordered scores are 6, 7, 12, 16, 17, 19, 19, 19, 21, and 23. Again, there is only one mode, 19. In problem 3.2c, the ordered scores are 6, 14, 14, 14, 16, 17, 18, 18, 18, and 28. The scores 14 and 18 both occur 3 times and are separated by the low frequency scores 16 and 17. Thus, this distribution can be described as bimodal. There are certain mathematical operations that are permissible for different levels of data. We introduced this concept in lecture 1b, but let's revisit it now that we have a firmer grasp on the meanings of the measures of central tendency. To find the mode, all we had to do was to get a frequency count for each of the categories. For example, if I were to count the students sitting in my high school physics classroom right now, yep, I'm multitasking, I would report a total of 9 students. If I reported them by gender, I would mark 8 males and 1 female. If I were recording these data in a spreadsheet with numbers and defined 0 as male and 1 as female, I could make a new cell labeled mean and have the spreadsheet calculate the mean. Would this value hold any meaning, though, as average gender? Of course not. While I could mathematically calculate the value, it wouldn't be appropriate to do so. Likewise, the median value would have no meaning because it wouldn't separate 50% of the data from the other 50%. However, it does make sense to say the mode equals 0 if 0 is clearly defined as male. So the only appropriate measure of central tendency for a nominal level set of data is mode. Ordinal data hold meaning with both the mode and median measures of central tendency. If there are 10 people in a track and field race, and 2 people tie for second place, then the data would look like 1, 2, 2, 4, 5, 6, 7, 8, 9, 10. Third place in this case disappears to account for the other 2 spots occupied by second place. For these data, the mode is 2 and the median is 5.5, because if you divided the data so values less than 5.5 were separated from those greater than 5.5, there would be 5 individual scores in each group, or half of the values. Thus, the median did what it was supposed to do. It divided all the scores in half. Most interval and ratio data, though, can have a mean calculated also. A characteristic of these data levels is the data are regularly spaced. So a mean value is a true representation of the center of the data. Now I say most interval and ratio level data because there are two instances where a mean is not an accurate representation of the data. The first case is if the highest and or lowest class interval is open-ended. For example, if you are describing a set of income data in which the highest category is marked as 100,000 or over, you cannot calculate the mean. This is because the category could include households who make just over $100,000 in a year, and it could also contain households who make several million each year, for example, Mitt Romney's. If you had all the original household incomes, you could calculate the mean because Mitt's income would have its true numerical meaning instead of being minimized to 100,000 for the calculation. The second condition for which calculating a mean can be inappropriate is if the distributions are skewed. According to USA Today, the average Broncos player's salary for the 2009 and 2010 season was just under $2 million. However, the player's median salary was about 50% lower, coming in at just over $1 million. The reason for this discrepancy is the really high salary players, for example, Champ Bailey, their salaries pull the mean to the right, hence the name skewed to the right. Thus, using the mean salary isn't a good representation of how much an average player earns. The median, which remember separates the lower 50% of salaries from the top 50% of salaries, is a much better representation of how the quote-unquote average player is paid. Before we move on, let's do a quick review of the measures of central tendency. Every data set has both a median and a mean. While these values may not be an actual number in the data set, they describe where the center of the distribution lies. When the median and the mean are close to the same value, the distribution assumes a symmetrical shape. The third measure of central tendency is the mode. Not all data sets will have a mode, and some sets may even have more than one mode. By definition, the mode is the most frequently occurring score in a set of data. If all values appear the same number of times, there is no mode for the data set. On a distribution, the mode would occur at the highest point in the curve because the height of the curve is a reflection of how many observations of that value are present. Imagine that the curve drawn in red is a smoothed out version of a bar graph. Now, think about the definitions of mean and median. The median, remember, separates 50% of the observations from the other 50%. If I were to shade in the region to the left of the median line in this graphic and compare it to the region on the right, it looks like they would have about the same amount of overall area. Along the same lines, the mean is the average of all the values. In this case, there are a few values on the right which pull the mean to the right. This is called a skewed graph because it is not symmetrical. The farther apart the values of the mean and the median are, the more skewed the distribution will be. To add another way to conceptualize the mean, think of it as being the balance point of the distribution. The blue triangles in this diagram act like a fulcrum. When there's an equal amount of weight on the left as on the right, then the curve will be balanced. Think about a hammer, or just go grab one and try it. Where will the hammer balance on your finger? That's right. It balances at the base of the hammer's head. That's because the mass of the hammer head is the same as the mass of the rest of the hammer. The same principle applies to distribution curves. The mean will lie on the curve so that the left and right sides offset each other. When the median and the mean, and the mode, if there is one, are all the same value or close to the same value, the distribution is symmetrical. If the symmetrical distribution looks like a bell curve, we call it normal. If the distribution is not symmetrical, it is described as either positively or negatively skewed. The trick to understanding how to classify skewed distributions is that you need to always look for the tail of this distribution. The mean is always closest to the tail in a skewed distribution. Remember, the horizontal axis is really a number line with the left side approaching the negatives and the right side approaching the positives. Thus, when the tail is to the right with the mean, it is positively skewed. If it were to the left, it would be called a negatively skewed distribution. So I'm going to tell you what these pictures are all about. This is my kitten, Mew, and she got her name because when I picked her up the first time, I actually had to pick her up by her tail. The backstory is that there was a neighborhood cat who had kittens and just a stray, and they were all out kind of playing around in front of my house, and so I started scooping up kittens so that I could get them to a shelter, and got all but one because this little girl hid in between the slats of the fence, and the only thing that I could get a hold of on her because she was so scared was her tiny little tail. When I picked her up by her tail, the neighbor who was watching all of this happen said, "You're so mean." And so me, being the ultimate geek, thought, oh, that's a good name for a kitten, Mew, because the mean, and picked her up by the tail. And oh gosh, even on a skewed distribution, remember, the mean is always closest to the tail. I know, it's cheesy. It's really cheesy, but it helps me remember that when I'm looking at a skewed distribution, don't focus on the hump. Focus on the tail. If the tail is to the right, it's a positive skew. If the tail is to the left, it's a negative skew. And the mean will always be closest to the tail. If there's a mode, it's the highest part, and then the median is going to be in between. So mode is highest, mean is closest to the tail, and median will be somewhere in between. All right, let's just make sure that we're all in the same place in terms of understanding the mean, the median, the mode, and the relationship between them. So let's look at a couple of curves here. In curve A, I want to decide what A, B, and C represent, if anything. A is the highest point on this graph, and I remember that the y-axis is a frequency count. So that highest point must be the mode. Now, I see that there's a slight skew to this thing, so that there's a tail on the right-hand side, and that tail is positive then, so it's a positively skewed distribution. And, I'll clear my mess here, I know that positively skewed distributions, the tail's on the right, therefore C must be the mean, because remember the mean is always closest to the tail. And then B, given that it's between the mode and the mean, must be the median. In curve B, I see that it's symmetrical, and therefore the only things on here that matter are matched up with line A. And that's going to be the mean and the median because it's symmetrical, and assuming it has one, also the mode. So B and C don't match anything. And then for part C, the tail is on the left, and I know that the left of the number line is negative. The tail is closest to the mean, so A must be the mean. C as the highest point is going to be the mode, and in between B will be the median. Here's just a summary of the 5 different general shapes. You have normal and rectangular as being symmetrical. Also in these symmetrical, remember the mean and the median will be the same, right in the center. Negatively skewed with the tail to the left, and positively skewed with the tail towards the right. And then you could also have a bimodal, and those humps might be equally sized, they might not. But the biggest thing is that there's a region or a score that has high frequencies separated by relatively low frequencies. All right, if you've been given values for the mean, the median, and the mode, you can figure out the skew. The thing I recommend doing is making sure that you recognize that there is a number line along the horizontal axes. So find your smallest number and put it farthest to the left. Find your largest number, put it farthest to the right. And then if you have more information, kind of put it eyeball where it would be in between-ish. Now I know that the 35 was for the mean. The median was 31. And the mode, 28. On the mode, you're going to go to the highest point of the curve. And this is skewed. And it's skewed to the positive or right side because that's where the mean is. If the mean is to the right of the median, then it's skewed to the right. Okay, let's try the next one. Same game. I'm going to find my smallest number and put it farthest to the left, and the largest farthest to the right, and then the other one's just kind of in there. The mode this time is 777, which means the hump is at the top. The mean is farthest to the left, median in the middle. The mean is to the left of the median, therefore it is left skewed or negatively skewed. And then finally, our third example. Our third example is most likely going to be a normal distribution. It's definitely symmetrical because we have a mean and a median that are the same. The fact that there's also a mode with that same value tells me that there is a frequently occurring score in the middle of a symmetrical distribution, which is almost always in this class going to be a normal curve. So here's a case where you've got the mean, the median, and the mode all in the middle. Okay, next example, we're just going to have a mean and a median to look at. The median is to the left because it's smaller of the mean, which means that this should be a shape that looks something like that, with the mean on the right means it's right skewed. On the right is the positive side. So the shape of the distribution is positively skewed. A reasonable value for the mode would be something lower than the median. Median came in at 44. So something for the mode, I don't know, 40. 40 would be reasonable. 35, there could be no mode. What wouldn't be reasonable is you wouldn't say that there is a mode of, say, 46. That would be wrong, because the mode isn't going to be between the median and the mean. Okay, last one. If I have a mode of 42 and a median of 55, 42 is less than 55, and I would expect the mean to be even farther to the right. This is a positively skewed distribution, and a reasonable value for the mean might be, say, 60.